Welcome. We're preparing to analyze a set of quite detailed technical documents you've provided. It's a thorough review covering Node.js architecture, its design patterns, and some core foundational concepts. This is certainly dense material, and our aim today is to carefully extract the key knowledge for you.
Indeed, and it's important to state upfront that this analysis we're working from was generated using artificial intelligence technology based on an advanced text about Node.js. Our intention here is to provide a slow, comprehensive, and professional discussion. This is really geared towards developers deeply familiar with the Node.js ecosystem.
Excellent. We'll structure our discussion following the source material, looking at it chapter by chapter. The goal is to pull out the crucial insights, the design patterns, and the fundamental knowledge presented in the text.
So let's begin with Chapter 1, which lays out the Node.js platform philosophy. It emphasizes pragmatism, simplicity, and what it calls the small core principle.
That small core idea seems quite central.
It really is. By keeping the built-in features minimal, Node.js effectively encourages innovation within the userland, that vast ecosystem of external modules. This decentralization means the community can experiment and iterate much faster, without needing changes to the Node.js core itself. It fosters flexibility.
And when we look under the hood at the internal workings, the analysis points to the reactor pattern. This seems to be the foundation for Node's single-threaded, asynchronous model. The core problem it solves is that issue of blocking I/O.
Exactly. Traditional blocking I/O is inefficient primarily because of how threads operate. If a thread has to wait for something like a network response or a database query, it just sits idle. But it's still consuming system resources, memory, and potentially causing context switching overhead. Since threads are relatively expensive, having them wait is wasteful and limits scalability.
So Node.js gets around this resource drain by implementing non-blocking I/O. But how does it achieve this consistently when operating systems handle I/O so differently?
Well, that's achieved through event demultiplexing. And the key component here is libouv. Think of libouv as Node.js's cross-platform abstraction layer specifically for I/O operations. It hides the underlying OS details, whether that's epoll on Linux, Q on macOS, or I/O completion ports, IOCP on Windows.
So libouv smooths out those differences.
Precisely. Now, one important detail the source highlights is that not all OS-level I/O is inherently non-blocking, particularly some file system operations on Unix-like systems. In those scenarios, libouv actually simulates non-blocking behavior by delegating those tasks to an internal thread pool. This ensures the main event loop, the single thread, is never blocked by those operations.
And looking at the language itself, JavaScript, the obvious advantage discussed is the universal stack using the same language on the client and server simplifies development and allows code sharing. Plus, outside the browser, Node.js grants full access to OS services through modules like S for files or Net for networking.
And for tasks demanding raw performance, the ability to integrate native C or C++ code using the NAPI is still very relevant. However, the analysis also points to a more modern alternative becoming prominent: WebAssembly or WASM. Compiling languages like Rust or C++ to WASM lets the JavaScript VM execute highly optimized code, often achieving near-native performance without the build complexity sometimes associated with native add-ons.
Okay, let's move on. The source material then shifts focus to modules, which are really at the core of the Node.js culture of extreme modularity. But it also introduces complexity, especially with two module systems coexisting, CommonJS or CJS, and the newer ECMAScript modules, ESM.
Yes, understanding CommonJS is fundamental. Its most defining feature is the synchronous require function. This synchronicity places a significant constraint. Module definitions themselves must largely execute synchronously. Another key aspect is CJS caching. This generally provides a singleton-like behavior, which is useful for sharing state.
But there's a catch with that singleton behavior, isn't there?
There is. You need to be aware that if the exact same package ends up being duplicated within your project's dependency tree, perhaps different versions required by different dependencies, you can actually end up with multiple distinct instances of that module. So the singleton guarantee isn't absolute across the entire application graph.
That sounds like a potential source of very subtle bugs. The analysis also mentions monkey patching in CJS. Could you elaborate on why modifying other modules at runtime is generally seen as poor practice?
Well, monkey patching introduces significant fragility. It breaks encapsulation, makes code very hard to reason about and trace, and tightly couples your code to the internal implementation details of another module. If that third-party module updates its internals, your patch will likely break. It's sometimes used as a last resort, but it's definitely not a recommended pattern.
So then we have the transition to ECMAScript modules, or ESM, which aim to standardize modules in JavaScript itself. The key features highlighted are a simpler syntax, better handling of cyclic dependencies, and crucially, asynchronous loading.
Within ESM, developers face a choice between named exports and default exports. The analysis suggests named exports are often preferable. They're explicit, which gives better support to development tools like IDEs for things like refactoring or static analysis. Default exports can be convenient for modules exporting a single main thing, but they can sometimes make automated tooling less effective.
And ESM has dynamic imports too.
Yes, the dynamic import function. It returns a promise, allowing you to load modules conditionally or on demand at runtime, which is very powerful for code splitting or loading optional features.
You mentioned ESM handles circular dependencies better.
Yeah.
How does that differ from CJS? Because CJS loops can lead to problems.
That's a key difference. In a circular dependencies scenario, CJS might provide a module object that is only partially initialized and exports object that isn't fully populated yet. ESM avoids this. It works with live bindings or references. During initialization, even in a loop, modules get references to what the other module will export. This ensures that once initialization completes, all modules have access to the fully initialized exports of their dependencies, sidestepping that potential incomplete state issue found in CJS.
All right, the next section in the analysis, covering chapters 3, 4, and 5, delves into what's arguably the most critical area for Node.js developers, handling asynchronous control flow. It starts with the most basic mechanism, callbacks.
Yes, callbacks are foundational. Simply put, a function passed as an argument to be executed when an asynchronous operation finishes. Node.js strongly standardizes on the error-first convention for these callbacks, where the first argument is reserved for an error object. However, the analysis immediately flags a major pitfall here, the concept known as unleashing Zalgo.
Unleashing Zalgo. That certainly sounds dramatic. What exactly is the danger there? Why is inconsistent timing so problematic?
It refers to functions that behave inconsistently, sometimes invoking their callback synchronously within the same turn of the event loop, and other times asynchronously deferring it. Imagine you call a function expecting it to return control immediately and call the callback later. If, under certain conditions, it calls the callback synchronously before your own code is even finished setting up, maybe establishing error handlers or releasing locks, you can get unexpected behavior, race conditions, and crashes. It violates the expected flow of control.
Okay, so consistency is key. The solution is to guarantee asynchronous behavior. The analysis mentions two main tools for this: process.nextTick and setImmediate.
They are both used to defer execution, but they operate as slightly different phases of the event loop. Process.nextTick schedules its callback to run on the microtask queue. This queue executes immediately after the current JavaScript operation finishes, but before the event loop proceeds to handle I/O events. It's very fast, very immediate, but if you queue too many nextTick callbacks recursively, you can potentially starve the I/O loop, preventing network or file operations from being processed.
It's setImmediate.
setImmediate schedules its callback for a later phase of the event loop, specifically the check phase, which runs after the I/O polling phase. This makes it generally safer in terms of not blocking I/O processing, as it yields to I/O events first. So, nextTick for urgent, immediate deferral, setImmediate for deferral that plays nicely with I/O.
The analysis also makes a point to distinguish callbacks, which usually signal a single result, from events. Events signal that something happened, and it might happen multiple times. This is based on the observer pattern, implemented via event emitter.
Correct. And with event emitter, a very common operational issue you need to watch out for is memory leaks. If you create listeners using bot or .add listener on event emitter instances that live for a long time, and you forget to remove those listeners using .remove listener or .off when they're no longer needed, those listeners and the closures they hold can stick around forever, consuming memory that the garbage collector can't reclaim.
Right, that's a classic trap. Now, Chapter 4 addresses managing sequences of callback-based operations. We've all seen or written callback hell. The text focuses on patterns to manage this flow.
Yes, primarily patterns for controlling execution order. Sequential execution involves running async tasks one after the other, ensuring completion in a specific order. This often requires patterns like a recursive iterator function to manage the chain of callbacks cleanly. For parallel execution, where multiple tasks can run concurrently and order doesn't matter, you might still need to limit the number of simultaneous operations. Patterns like using a task queue help manage concurrency, preventing you from overwhelming system resources by firing off too many operations at once.
Then Chapter 5 introduces the evolution beyond callbacks, promises, and the current standard, async await. Promises were a huge step forward, weren't they?
Absolutely. Promises provided a much cleaner way to handle asynchronous sequences through chaining, and crucially, they offered more robust and composable error handling via .catch. They largely solved the structural problems of callback hell.
An async await build on top of that.
Exactly. Async await is essentially syntactic sugar over promises. It allows you to write asynchronous code that looks and behaves very much like synchronous code, making it significantly easier to read and reason about. It also acts as a natural guard against that Zalgo issue, as await always ensures an asynchronous yield point. The source also mentions the promisification pattern wrapping callback-style functions to return promises and notes some complexities, like building non-leaking infinite loops using promises, which requires careful structuring, often using, while true, with an await inside to yield control correctly.
Let's shift focus now to Chapter 6, which covers streams. In a platform so focused on I/O efficiency like Node.js, streams seem absolutely critical. The key benefit highlighted is constant memory usage.
That's the main advantage. Whether you're processing a tiny file or a terabyte-sized data set, a well-designed stream pipeline uses a relatively small, constant amount of memory. This is possible because data flows through in chunks, and streams can be composed together using methods like .pipe.
The analysis details the four main stream types: readable, writable, duplex, and transform. But it puts special emphasis on the concept of back pressure. Can you explain that?
Back pressure is the mechanism that prevents a fast readable stream from overwhelming a slower writable stream. Think of it like flow control. When a writable stream's internal buffer fills up beyond a certain threshold, called the high water mark, its write method will return false.
So that false is a signal.
It's an advisory signal. It tells the readable stream, or whatever is writing to it, hey, slow down, I'm full right now. The producer should ideally pause sending data. Once the writable stream has processed some of its buffered data and the buffer level drops below the high water mark, it emits a drain event. That drain event signals to the producer that it's safe to resume writing data. Respecting this back pressure mechanism is vital to prevent excessive memory consumption from ballooning buffers.
And for composing streams together safely, the source recommends using the pipeline function over just .pipe. Why is that preferred?
Primarily for better error handling and resource cleanup. If an error occurs anywhere in a chain created with simple .pipe, it doesn't automatically destroy all the streams in the pipeline. This can lead to resource leaks. Pipeline, however, ensures that if any stream in the sequence errors or closes prematurely, all other streams in that specific pipeline are properly destroyed and cleaned up. It's much more robust. The chapter also touches on using streams for async control flow, like sequential iteration with readable.from or implementing parallel stream processing.
Okay, now we move into the more traditional software engineering patterns covered in Chapter 7, 8, and 9, but specifically how they apply within Node.js. Chapter 7 deals with creational patterns.
Yes, starting with the factory pattern. It's widely used in Node.js to decouple the process of object creation from the code that uses the object. This allows for flexibility, like creating different object types based on environment variables or configuration, and helps enforce encapsulation, perhaps using closures to hide internal details. The builder pattern is also relevant when you have objects with many configuration options or parameters. It provides a fluent, step-by-step API for constructing complex objects.
The revealing constructor pattern sounds particularly interesting in a JavaScript context.
It is. It leverages closures to provide stronger guarantees about object initialization. Certain sensitive properties or methods of an object are exposed only to the constructor function itself during the creation phase. Once the object is constructed, these internals are no longer accessible externally. This is useful for creating truly immutable objects or objects where initial setup requires privileged access that shouldn't be available later.
Moving to Chapter 8, structural patterns. These deal with object composition. Let's start with the proxy pattern.
The proxy pattern provides a surrogate or placeholder for another object to control access to it. In Node.js, this is useful for implementing things like validation, checking arguments before forwarding a call, logging, or even more complex scenarios like lazy initialization or creating reactive objects that automatically track changes the school. Change observer pattern is often implemented using proxies.
Then there's the decorator pattern. How does that differ?
The decorator pattern focuses on dynamically adding responsibilities or behaviors to an object without altering its core structure. This is often done through composition, wrapping the original object. Think of adding logging or caching capabilities to an existing database client, or how frameworks like Level UP use plugins to extend functionality.
And the adapter pattern.
The adapter pattern's goal is to allow objects with incompatible interfaces to work together. It wraps an existing object and exposes it through a different expected interface. A common example might be creating an adapter that makes a specific database look like it conforms to the standard Node.js FS file system API, allowing file system tools to interact with the database.
So to summarize the distinction, proxy controls access with the same interface, decorator enhances behavior with the same interface, and adapter changes the interface.
That's a very good summary.
Finally, Chapter 9 covers behavioral patterns, focusing on communication and algorithm assignment. The strategy pattern seems quite fundamental.
It is. The strategy pattern allows you to define a family of algorithms, encapsulate each one, and make them interchangeable. This means the algorithm a system uses can vary independently from the clients that use it. A common Node.js example is handling different configuration file formats. You could have separate strategies for parsing JSON, YAML, or INI files, and select the appropriate strategy at runtime based on the file extension. The state pattern is closely related, often considered a variation of strategy, where the object's behavior changes based on its internal state, and different state objects encapsulate that behavior.
The middleware pattern is also mentioned, which feels very familiar in Node.js web development.
Extremely relevant. Middleware creates a pipeline of processing functions. Each function receives data, like an HTTP request, performs some action, and then either terminates the processing or passes the data along to the next function in the chain. This is the core mechanism behind frameworks like Express or Koa for handling requests, authentication, serialization, etc. Lastly, the command pattern encapsulates a request or action as an object. This decoupling allows for queuing commands, logging them, supporting under-rato operations, or even sending commands over a network for remote execution.
All right, let's synthesize the final block of chapters 10 through 13, which cover more advanced topics, scalability, and architecture. Chapter 10 discusses universal JavaScript.
Universal JavaScript, or isomorphic JavaScript, refers to code that can run both on the server and in the browser. The main challenge discussed is managing platform-specific code effectively. Solutions often involve build-time techniques like module swapping using tools like Webpack, where different implementations of a module are bundled depending on the target environment, Node.js or browser. Architectural patterns like two-pass rendering in React or async page loading are used to optimize the user experience by doing initial rendering on the server.
Chapter 11 gets into advanced production recipes. One common issue is dealing with components that need asynchronous initialization. How is that handled?
Several patterns apply. You might use a temporary queue to hold requests until the component is fully initialized, or implement the state pattern where the component transitions from an initializing state to a ready state. Another critical recipe for performance is asynchronous request batching and caching. If multiple identical requests arrive concurrently for an expensive operation, batching ensures the operation runs only once and all requests receive the same result, often cached using promises.
And it revisits the challenge of CPU-bound tasks in Node's single-threaded model.
Yes, it outlines the main approaches. One is to break down the long-running computation into smaller chunks and interleave them with set immediate calls, yielding control back to the event loop periodically. Another is to offload the entire task to a separate child process. And the third, increasingly popular approach is using worker threads, which allow for true parallelism for CPU-intensive work within the same Node.js process, managed more efficiently than child processes for certain tasks.
Chapter 12 focuses squarely on scalability and architectural patterns, referencing the scale cube model.
Indeed. The x-axis, horizontal scaling or cloning, is where Node.js typically shines due to its stateless nature. Running multiple instances of your Node.js application behind a load balancer provides high availability and fault tolerance. Techniques like zero downtime restarts, often managed using the built-in cluster module, are crucial for maintaining service during deployments. The y-axis involves functional decomposition into microservices, leading towards distributed architectures.
And managing those distributed systems requires more infrastructure.
Absolutely. When you move to microservices, you need mechanisms like service discovery or a service registry like console or etc. So services can find each other, and container orchestration platforms like Kubernetes become essential for managing deployment, scaling, and health of these distributed services.
The final chapter reviewed, Chapter 13, covers messaging and integration patterns, how these distributed components communicate reliably. It starts by distinguishing message queues from streams.
Right. Message queues, often based on protocols like AMQP, think RabbitMQ, are typically used when guaranteed durable message delivery is paramount, even if a consumer is temporarily offline. Streams, like Redis streams or Kafka, are more focused on handling ordered sequences of events or data records, often at very high throughput, where consumers won't track their position in the stream. The analysis also contrasts peer-to-peer messaging systems like ZeroMQ, which offer low latency without a central broker, versus broker-based architectures which provide more durability and complex routing options.
And it details several common messaging patterns built on these systems.
Yes, patterns like publish-subscribe for broadcasting messages to multiple interested consumers, fan-out fan-in for distributing tasks across multiple workers and collecting results, and importantly, how to implement request-reply semantics over asynchronous messaging. Since messaging is often inherently one way, building a request-response interaction typically involves the correlation identifier pattern. The requester sends a message with a unique ID and specifies a reply queue. The responder processes the message and sends the result back to the specified reply queue, including the original correlation ID so the requester can match the response to its initial request.
This has been a very thorough walkthrough, connecting those fundamental Node.js mechanics like the event loop and modules all the way up to complex patterns for distributed systems and scalability. You should now have a much stronger grasp of the foundational knowledge surrounding Node.js design principles and architectural best practices discussed in the source material.
The analysis provides a solid framework, but the original source text itself contains extensive code examples and much deeper contextual explanations for all these patterns and concepts. To truly solidify your understanding and see practical implementations, we really do recommend acquiring and reading the full book.
We certainly encourage you to subscribe for more analyses like this one as we continue to explore complex technical source materials. We hope this has been valuable for you. We wish you a great day.